Hello, so in this video we will talk about something called a pumping lemma, which is a property of regular languages. So the statement goes like this. So if we have a finite state automaton defined as usual by S, the set of states, I, the input symbol, F, the mapping, S0, the starting state, and F, the set of accepting or final states, if this is a finite state automaton, and we have a string X, which is a member of the language of that finite state automaton, such that the length of that string is more than the number of states, then we can write our X as UVW, where the following holds. So UVW are members of I star. So UVW are members of I star, and what does I star mean? I star means the combination of all the strings we can find from our input symbols. Okay, and then the length of UV means U concatenated with V, is less than or equal to the number of states, and length of V is at least 1. So if this is true, then we can also we can also conclude that U, any concatenation of V and then W, they are also a part of languages. So for example, if it means that if we have 0 0 1 0 1, and this is my, for example, V, this is my W, and this is my U, then 0 0 1 0 1 and 0 1 should also be in the language, because this is V squared, or V concatenated 2 times, and then so on. This is also in the language. So if this is in the language, then this also has to be in the language. So this is what the explanation of the statement is. Okay, so now let's start with the proof. So for the proof we need a node to remember, which is that if we have a finite state automaton, for example, if we have, let's say this is a state A and we have 1 here. So this, what does it mean in the language form? It means that we can have 1. So there is some path here, there's some path here. So that path can have any number of ones. It can have 0 number of ones, it can have 1 number of 1, or it can have like 1000 number of ones, or it can have any number of ones here. So what does it mean? We write a path starting and ending at the same state represents Clean's closure. So this we already know from our proof of so the so-called Clean's theorem, but this since we are going to use it, so I just write this as a note to remember. Okay, and then starting point, we said that we have the length of X is greater than or equal to our number of states. So we, without loss of generality, we can assume that this is equal to n, and then once we see the proof, you can appreciate that it holds for any length which is more than this number. Okay, so now let's say we have a path driven by the string X, so on the finite state machine. So we start with S0. So this is my S0. Okay, so this is my S1. Okay, and then also let X, this is equal to A1, A2 up to AN, because X has the length n. Okay, so this is my A1, this is my A2 going to S2, and then we have the last is Sn, and this is my An. Okay, and this, since it stops here, this is in the language, so this has to be what? This has to be a final state or accepting state. Okay, okay, so with Sn classified as a final state, but this is a problem with this. Now we have how many states here? We have S0 to Sn, so this is what this requires us to have n plus 1 states. Okay, so then this guy is An. Okay, so then this means that since the number of states is n, at least 2 of them should be identical. And where does this postulate come from? This comes from our good old pigeonhole principle, which says that if we have more pigeons than holes, then we can have at least one hole should have more than one pigeon. Okay, so then we have more states than we are places for the states, so that means that at least 2 of the states must occupy the same symbol, let's say like this. Okay, so then this means that we assume that some Si and some Sj are identical, where I and I less than j. This is again without loss of generality. So then we have a path starting at and ending at the same state, right? So we have a situation like this. So we say this is my S0, this is A1 goes to S1, and then we have this is AI going to Si, and then we have the situation like this. We have AI plus 1 going back to Si, and then I have AI plus 2 going to Si plus 1 up to, now I can have Sn minus 1 and then An here. Okay, so then this n minus 1 is now my final state, obviously. Okay, so now note that this situation tells us that A1, AI plus 1, AI plus 2, An is actually in the language of the finite state automaton, language of M. So this means we can say that X, this is equal to AI, A1, A2 up to AI plus 1, AI plus 2 up to An. This is in the language of M. Okay, but this loop means what? This loop means that any concatenation of AI plus 1 will also be in the language of M, because I can have A1 up to AI, then I can have any number of AI plus 1s, and then that will also be in the language. So we can say also A1, A2 up to AI plus 1. So any number here, AI plus 2 and An. This is also in, so this is also in the language of M, correct? So now I can go back to the statement of the proof. I can call it U, I can call it V, and I can call this guy W. So I should have said this one here, U here. So this is my what? Vi, and this is what? W. So this means that U, Vi, W is also in the language of M. Okay. So now based on where we have the loop, then we can determine our loop here. So now what if, so this is for the length equal to n. So although it's very straightforward, but for the sake of generality, let's do it for if we have Lx, this is equal to n plus 2. So then the situation looks like this: S0, S1, and then Si, and then Si plus 1, then Si plus 2, and so on, Sn. So this is my A1, this is my AI, this is my AI plus 1, this is my AI plus 2, this is my AI plus 3, this is my AI plus 4, and this is my An plus 2. Okay,
The last
and then
state
you
should
can
be
appreciate that
Sn
now
minus
our
1,
U will
and
be
the
again
last
A1 to AI, our
transition
V will be
input should be An
AI
plus 1.
plus 1,
So this is
AI
actually
plus
for
2,
length
AI
n
plus 3,
plus
and our
1
W will be
and
AI
not
plus
n
4
plus
up
2.
to An plus. This is just plug and play here. So based on the length you want to construct, you can make a loop like this. I mean, as desired. Okay, and this is not the only answer. I mean, you can make a loop with one Si, and then you can make another loop with, for example, I plus 7 or something like this. But this is one of the ways you can do it. Okay, the point is that decomposing X into U, V, and W, you can see that U and then any concatenation of V followed by W will also be in the language. Okay, this is the whole point. Okay, and then this guy, because this is the minimum length for which it holds, This is also known as the pumping length. Okay, so this is the statement and proof of the pumping lemma. So now let's see whether we can prove something, use pumping lemma to prove or disprove something. So now let's write it down like this. So what do we have? We have if P implies Q, then not Q implies not P. These are equivalent statements. But does it mean that not P implies not Q? No. So we can actually use the pumping lemma to incorporate this guy but not this guy. Okay, so what does it mean? It means that if our P is, so a language is regular. This is my P. And then, so this is my P and satisfies pumping lemma. This is my Q. So, and this means that we can actually prove that any language is not regular by using pumping lemma. We cannot use pumping lemma to prove a language is regular. So then this means that this guy, we can say if a language does not satisfy the pumping lemma, then it is not regular. Okay, we cannot say that if a language is not regular, it does not satisfy the pumping lemma. Okay, so there may be some languages which are not regular and still satisfy the pumping lemma, but definitely if a language does not satisfy the pumping lemma, it is not regular. Okay, so now this is, let's say we have a language like this. We have a language 0 and then followed by this guy. So let's call it B. So what does it mean? What kind of strings are contained in this one? So n is greater than or equal to 0. Okay, so obviously empty string is contained, and then 0 0 1, because 2 zeros and 1 1, then 0 0 0 0 1 1, then 4 zeros and 2 ones, and then so on. So we have double the number of zeros than the number of ones, and so on. So this is the number, this is the type of strings we have in B. Okay, now we have to prove that this guy, this language is not regular. So then our strategy is that we will prove that this set of strings, they do not satisfy the pumping lemma. Okay, so let's say let x belong to B. Okay, so then if we can write and x is equal to u v w. Okay. So now the first observation is v cannot have 0 1 in it. Is it true? Why? Because if we have to satisfy the pumping lemma, then any concatenation of v should also be in B, right? Any concatenation of v should also be in B, right? So but if we have this, then what is v squared? V squared is 0 1 0 1. But 0 1 0 1 will never be the case, because the moment we have 0 1 here, we have all ones. So once we reach a 1, we cannot have any 0 followed by it. Okay, so this means v is all zeros or all ones. Okay, but then there is a problem here, because u and w are fixed, right? So then v, any power of v with I greater than 1 will destroy the symmetry, destroy the order. What does it mean? It means that, let's say we assume that v is equal to, and we said that for example we say x is equal to 6 zeros and 3 ones, and we say that okay, my v is this guy, my w is this guy, and my u is this guy. Then what is u v squared w, right? So u is still the same, v squared is now 6 zeros, and w is just this guy. But this destroys the symmetry, because remember, the next string will have double the number of zeros here. Okay, so then we cannot tamper with W, we cannot tamper with U, but we can tamper with V, and we can actually satisfy the number of zeros, but the W will make sure that the number of ones will not increase at all. So this means that without using 0 1, we cannot make sure the number of zeros and ones are consistent. But with using 0 1s, we will destroy the order of this, because once we have a 0 1, we cannot have another 0 followed by it. So this means that this language, so we can say B does not satisfy the pumping lemma. This means B is not regular. Now there is something to add a final note with. We said our finite states automaton. So we also, implicitly we have taken make use of the Clean's theorem here, that if our language is regular, if and only if it can be represented by a finite state automaton. So although we started with the finite state automaton, we can also set the pumping lemma that a language is regular. If a language is regular, then it satisfies the pumping lemma. Or we can say, if a language does not satisfy the pumping lemma, it is not regular. Okay, so this is it about the pumping lemma, its statement and proof, and a demonstration that a language, how can we check whether a language is not regular using the pumping lemma. Okay, hope it was easy to understand, and thanks for watching. Hope you liked the video.